Made you wait for it. Now, so if I'm not mistaken, this is where we left it the last day. I had introduced you to the idea of dithering. So you need dithering because you are reducing the number of bits required to represent each pixel by reducing the number of different colors that are in the image. If the number of colors in the image is smaller than the number of colors you have available in your color palette or in your color lookup table, then the problem is trivial. But if the number of colors in your image is greater than the number of colors you have available, then something has to give. One way they can give is that you force the colors of the pixels to be the closest match that's available in the color lookup table. However, dithering allows you to cheat somewhat. And what you do with dithering is you simulate the desired color by the juxtaposition of pixels in available colors. And if you get the order right, it'll have the appearance of the desired color. So if you wanted gray, but you didn't have gray, but you had black pixels and white pixels, it would be possible to combine them in such an order that you would have the illusion of gray from a distance. So if you had black pixels and white pixels in a chessboard pattern, you could see how that would give you the illusion of a 50% gray. Does that make sense? So conceptually, that's all going on. What we're going to do now is we're just going to look at some of the maths that would explain how that works in the RGB space. But it's really the same thing. If you have pixels that are fully red and pixels that are not red at all, and you rearrange them in a chessboard pattern, then their redness would be the average of the redness of the pixels. They'd be halfway. Just as the black pixels and the white pixels would give you 50% gray, the fully red pixels and the not red at all pixels mixed in the same ratio would give you half red. So that's all we're doing. So looking at this example here, we have the original color on the left. I don't know why I always turn to the screen and show people my head when I can see it here. It's a habit. So the color on the left there is the original plain color, and then the color on the right, there's some dithering going on there to simulate the color. Can you see it on the screen? Can you actually see the pixels? Depends, just about. If you have glasses and you take them off, it's a no-brainer. But if you can see well, no. So here what I've done is I've blown up the pixels here. And so it's more obvious now. And if I take my glasses off, even at this distance, they look the same. The important thing is that they appear to have the same color from a distance. Now, in fairness, this is quite subtle. Well, not that subtle either. Okay. Now, let's consider this scenario here. In reality, they're typically more random, but for our maths exercises, we want regular patterns. So here in this chessboard pattern, there's obviously they're in a ratio of 50-50. So the dithered color is going to look like the average of the colors that make it up. So like if it's black pixels and white pixels, then on average it's going to look gray. How does that work then in RGB? We have to take the red and the green and the blue separately and consider them each individually. So here the redness of the light pixels is 187 and the redness of the dark blue pixels is 51. So the average redness is 119. The greenness of the bright pixels is 225 and the greenness of the dark blue pixels is 51. So the average greenness is 138. And similarly then with the blue, we've 227 and 153, giving us an average of 190. So the simulated color is this shade of blue here in that chip. And that makes sense. If you mix that light blue and that dark blue in a 50-50 ratio, you would expect to get something like that. Unfortunately, my vision is so good that even if I take off the glasses, the color doesn't quite, well, actually it's just so bad that, you know, the whole screen merges before the pixels merge together. But you could see how these could become that. I think that's plausible. Let's consider this here. So on the left here, we have this shade of pink. And on the right here, we have the same shade of pink that's been simulated using dithering. And so we have a slightly darker pink and a slightly lighter pink, which when averaged out will be equal to this shade. Let's see the math there for how that works. This is a somewhat contrived example because I've kept the redness values and the blueness values for both shades of pink the same. So if the redness of the dark pink is 255 and the redness of the light pink is 255, well, working out the average of those is quite easy. It's going to be 255. Similarly with the blueness, if the average blueness is 205 in one, sorry, if the blueness is 205 in one and 205 in the other, then the average is going to turn out to be 205. Where it gets more interesting is in the greenness. So the greenness of the light pixel, the bright pink, is 153. And the greenness of the dark pink is 102. But in this dithering pattern, they're not in a 50-50 ratio like in a chessboard. There's one light pink for every 3 dark pink pixels. So when we're working out the average greenness here, we have to count the greenness of the dark red pixels, the dark pink pixels, 3 times. So it's 153 plus 102 plus 102 plus 102 all over 4. Or if you're being slicker about it, it's a weighted average. Let's have a look at this one here. We've got 3 colors in a pattern, and that dithering pattern is trying to simulate some desired color that isn't in the lookup table, that isn't in the palette. What's the simulated color? What's this going to average out to be? Well, the first question we have to ask is what's the ratio of the different colors? If it was a chessboard pattern, it would be obvious and they would be equal. But here it's looking to me like there are 2 A's for every 1 B and C. So we need to count the A's twice. So to do this, we need to work out the average redness. We just consider the red, and then consider the green, and then consider the blue. So if the A's have a redness of 200, the B's have a redness of 200, and the C's have a redness of 0, what's the average redness when you have 2 A's, a B, and a C? Well, you count the A twice, so you got 200 plus 200 plus 200, all divided by 4, isn't it? You got 200 plus 200 plus 200 plus 0, all divided by 4. It's 150, isn't it? Does anybody want to work? Yeah, you can.
Yeah, I sort of missed that. I missed it there. How can you count 200 twice in the A?
Because there's two A's. If we consider the smallest repeating pattern, we've got two A's, one B, and one C. Okay? Now, if you were doing weighted averages, you could also count up the fact that there are like that there are whatever 64 A's and 32 B's and 32 C's. It doesn't matter as long as you keep the ratio the same. Let's figure out what the ratio is. Yes, sir.
It wouldn't matter that the B is there in three lines and C is in two.
I don't understand the question.
There's 3 lines.
Is it more complex than it looks?
12 B's and 8 C's. Would you have to account for that as well?
Are you talking now just about...
Position.
Sorry, no. There's two possible explanations here now, or there's two possible meanings of your question. Is this more complex than I think it is? Am I making a mistake? Or are you just talking about the fact that we run out of tiles, that the display is so small we're just seeing them not quite in the ratio they're there?
That would be it.
Like, this is representative of the dithering pattern.
Okay.
In reality, it might be 20 times bigger than this in each direction. So you're just talking about this last line here.
No, it's just he's saying that
There's 12 B's and 8 C's.
and there is more A's.
No, there's 3 lines of B's and 2 lines of C's.
Yes, but that's just because we were only looking at 5 lines.
Okay.
Alright.
So it's only just part.
This is representative. So if you saw this in an exam, for example, you would be expected to understand that the repeating pattern is ABCA. That's 4 there being repeated over and over again. It's just that we're not displaying the next line, nor are we displaying the next columns.
Oh, I see. They're in groups of 4.
So like
Yeah.
groups of 4,
Yeah. Get the idea? No, actually, in practice, the dithering may be very regular in nature, or it can be more random. And you can even set that. You can even say to Photoshop, actually, I have a preference for a particular kind of dithering, if you want. But if we were looking at a random situation, then we would actually have to go and count them in the sample that we have. If we had something like this one here, we'd just have to go accounting and see what we get. But in this situation, it's contrived. No, it's not unrealistic either, but just to make the maths, just make it obvious what's going on. So, I think I've answered that question anyway. So we're talking now about 2 A's, 1 B, and 1 C. So, thinking about the greenness, how much greenness is there on average? What's the total?
160.
Is it 160 now or something else?
210, isn't it?
It's not 110.
160 divided by 4, is it?
Where'd you get 160 now though?
100 plus 10 plus
50.
Plus 50. The 2 A's. Yeah. So you're talking about 210 divided by 4 is whatever. And the blue works out, I think, at 38. So the simulated colour then would be 150, 53, and 38.
Do you always round up, or do you round down as well?
It doesn't really matter, but obviously you can't have a decimal value.
Yeah.
You can't have an intermediate value. And that's the thing with dithering. Even with the colours you have available to you, you're probably not going to hit it perfectly. But as we discussed, human vision being what it is, the difference between colour 16 million and shade 16,000,001 is probably so slight that we wouldn't be too concerned about it. And also, if you could combine 2 or 3 colors to get very, very close, or combine 6 colors in a pattern to nail it, the overall effect of the 3 colors in the dithering pattern might be preferable to the 6 colors. You know, you don't know. So there's a whole art and science of dithering, and we've largely decided to let Photoshop worry about it. When I first started in the multimedia business, we all spent an awful lot of time worrying about how we were doing our dithering. It's less important now. See, in the early days, your display could only display 256 colors at any one time. That's all you had. So if you had one image on the screen that had a particular palette, and you had another image you couldn't display both on the same screen unless they had the same palette. So if you were going to display lots of images, you know, an interchange between them, if you had, say, 20 images, you would be worrying about not just the best palette for any one individual image, but the best palette for that entire set of images, so that you could transition between them. Now, mercifully, you'll never have to worry about things like that. Although it always surprises me how worries that once were old become new again. Like, the last time I would have had to worry about palettes was if you're doing, you know, images on a Nokia or a ye olde Nokia, where you didn't have 16 million colors. Or if you were trying to do something on a handheld console not so long ago, you wouldn't have had the full 16 million colors. So some techniques, you know, as things that were once impossible move to more basic platforms, sometimes old constraints are reintroduced. So the same with some video compression issues that we'll be looking at. There was a time you could only do video compression in software very slowly, but then it became possible to do it in real time in hardware. But then as it became a domestic thing, it became a software issue again. So some of these things, you know, you think, I'll learn this and then I'll never need to use it again, and then, you know, you may be at some time in the future asked to put some images, to embed images in clothing that changes color depending on an app on the person's phone. And let's imagine, for example, I'm glad I thought of this example now. Let's imagine, for example, that the technology is such that you can only change the color of your shirt to 16 different possible shades. You might have to design the program that allows the user to simulate any color. Looking at your shirt there, I think that's what inspired me to come up with that example. So, you know, these things this may yet darken your door again, and you'll think, haha, I thought I was done with that. And certainly I thought I was done with it, and it's largely an interesting academic exercise now. And we're only interested in it because the GIF format is still with us, and GIF does this. Just to test your math skills more than anything else, here we have a simulated color that is 260/80. There are X pixels, Y pixels, and Z pixels. We know what X is, we know what Y is. What's Z? So again, the ratio is the same, isn't it? 2 X's, 1 Y, and 1 Z. Thinking about the red is easy, isn't it? Because, I mean, if it has to average out at 200, if the X's are 200 and the Y's are 200, well, it's a no-brainer to know that the Z's should be 200.
200, yeah.
So the red is easy. The green, not so much. So if you had 4 pixels that were going to average out at 60, then what would the total of them be? 240, wouldn't it?
240, yeah.
It's 4 of them. So 240. So it's all going to add up to 240. The 2 x's add up to 100, and the y is 10. So you've got 110 from 240. Is that 130? I hope I'm right. So you can reason it out that way. A more sensible approach algorithmically would be to just kind of do the calculation with the weighted averages. If you're comfortable with algebra and stuff, you end up doing something like this, with your 2x and your y and your z and blah, blah, blah.
I don't understand blue being 220. I don't understand blue being 220.
We see now it could be wrong. It could be as wrong as the red.
I thought it was 140.
I think it's 120 for the green.
I think it's 130. I think we reasoned out it was 130. I can understand my maths being wrong. I wouldn't like my logic to be wrong though.
Blue 140.
What's it supposed to be now for blue is 80. So you can see how if you've got 2 20s and a 60 and you want it to average out at 80, it certainly needs to be cranked up a notch. If it's going to average out at 80, that Z has a lot of compensating to do, doesn't it? If you could imagine you've got 3 assignments, you want to get a mark of 8. You want to get a mark of 80. You got 20 in the first part, or the first 2. You got 60 in the next one. To average out at 80, actually, you're probably not going to happen. Probably more than 100. Let's see. What does 220 sound plausible?
I thought it was 120.
Yeah. It's easier when you multiply
The thing by 4.
by 4 and
Yeah,
then you just
yeah.
subtract it.
Yeah. So 80 multiplied by 4 is 320. You need 320. And you've already got 100 of that then gone. So you have 220 left. Okay, so that's dithering. So I won't belabor that now, and we still have time to tackle something else. I think I will keep you a bit longer because while there's no pressure, we are a little bit behind in terms of where everyone else is. So what I'm going to talk about now is GIF, and the fact that GIF is still with us is the only reason we're even interested in dithering. GIF is still will be considered one of the standard formats for images. So although an application like Photoshop allows you to save an image in a multitude of formats, if you're putting it on the web, GIF, JPEG, and PNG are the only 3 that would be considered standard.
What's the GIF stands for?
What does GIF stands for? GIF stands for Graphics Interchange Format. I thought you were going to ask me the trick question of is it GIF or is it GIF? So some people call it GIF, some people call it GIF. I think the GIF people are right, but they're still tools. So in Ireland anyway, people call it GIF. But you will get nerds arguing in the pub about whether it should be GIF or GIF. And I think technically the GIF people are probably right. But that was the argument I'd use, but I think the person that actually devised it called it GIF, not GIF.
When you say the GIF file, is it capital G?
That doesn't matter. That would be an operating system issue. So the question is, when you save it, does it matter if it's capital G or not? No, but yes. So depending on the operating system, remember we had this conversation way back when we were talking about FTP, where the operating system of the web server may be case sensitive. And in most cases, it is case sensitive. So you want to go with all uppercase or all lowercase or whatever naming convention you want, but be consistent. So in that sense, it would make a difference.
I was just saying because the pronunciation of a capital G is different to a small g. That's probably where the argument comes from.
That would be a stretch, maybe. I don't know. No. So in summary then, things you can do with a GIF. So GIF uses at most 8 bits per pixel, which by today's standards, today's graphic designers would find that very constraining. Okay? So GIFs then can have at most 256 colors. But we have the option of them being any 256 colors that we like. So that can work well or not depending on the image that's being coded. And dithering can help depending on the context also. Once you've converted to the 256 colors, once you've gone from RGB to indexed color, once you've done that part, the rest of GIF then is lossless. So GIF per se is lossless, but to be, at the GIF races, you may have to introduce some loss to get your pixels in the space that you need them to be. One color may be transparent. There's a progressive option also. And you can have an animated GIF. And animated GIFs are very interesting. I think they're a testament to people's, ingenuity. I mean, I remember seeing animated GIFs many, many years ago and being blown away, video on a computer. Oh my God, The constraints, the creative constraints placed on people by animated GIFs have sort of been embraced. And there's been a kind of a resurgence in the use of animated GIFs as a sort of an art form or a subgenre of video. And we're kind of seeing that, that aesthetic being revived again now by Vine, which is a Twitter app, I think, that lets you capture just 6 seconds of video. But that's a different thing now, but I feel like it's channeling the animated GIF there. So GIF is ideal for logos and graphics and buttons. So if it doesn't use too many colors, especially if it's less than 256 colors, well then GIF is very handy. There's no issue there. So the quality will be preserved. The only issue is that if you need more than 256 colors, you may run into problems. So anywhere where you have limited colors or where you have plain expanses of color, GIF is ideal and preferable to, say, JPEG, which we'll learn about in the next class. One of the things GIF does, and it's just one of the things it does now, but it's the main thing GIF does when it's coding an image, is it uses run length encoding. And in run length encoding, what you do is you replace multiple occurrences of something by that thing and the number of times it occurs. So let's say I was to turn off the screen, or turn off your screen, and I was going to get you to redraw this sequence of pixels on graph paper with, coloring pencils or something. I could go blue, 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 red, 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 green, 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 and keep going like that. But clearly it would be more efficient if I was to just say there's 4 blues, 15 reds, 20 greens, and 1 more blue. It would achieve the same thing much more efficiently. And that's the main thing that's going on in a GIF. So you could see how if you take, say, the CIT logo there, at the very, very top of that image, it's just a whole row of white pixels. And another row of white pixels. And eventually we have a bunch of white pixels, and then a whole bunch of red pixels, and then a bunch of white pixels again. So apart from the fact that the CIT logo has very few colors in it, they're also all lined up in a row, which kind of helps. So this begs the kind of interesting question here that I'm posing. We have two images which are identical, except one has been rotated 90 degrees right. So one of them, if it was coded using GIF, would be quite small because it's a best case scenario for run length encoding. And the other one, if coded using GIF, would be a bit bigger because it's pretty much a worst case scenario. No, actually, best case scenario for GIF is just like a whole image with one color in it, you know, but short of that, one of these is a best case scenario and one of these is a worst case scenario. So which one would be the big GIF and which one would be the small GIF? The big is on the left, A, and the small one is on the right, B. Because if I was to call out to you pixel by pixel what B was made up of, I could go, well, it's such and such a light shade of blue, and there's 200 of those. And then in the next line, it's a slightly darker shade of blue, and there's 200 of those. So it's ideal for run length encoding. A, on the other hand, every single pixel, one after the other, is a different color. So I'd have to go, well, that's a light shade of blue, then a slightly darker one, then the slightly darker one, then the next darkest one, and then the next darkest one, and eventually black. And then I'd repeat that 200 times. It would be the same thing 200 times, but GIF isn't in a position to capture that kind of thing.
Could it go vertically?
No. I mean, it could if we could go, you know, I mean, you could design it that way, but GIF doesn't do that. Interestingly, fax machines use run length encoding. Or used, I don't know if, I mean, I saw a fax machine recently, or I think there's one left in CIT, just in case. But the way people would have cover pages, or used to have cover, well, you're probably too young even, but you'd have a cover page on a fax. Or let's say you had a black and white document that you were faxing a lot. If you had lots of horizontal lines, you were okay, but if you had lots of vertical lines, it was actually going to be much slower and take longer and cost more money, but I digress. So run length encoding then likes long runs of the same color. Of course, if that same color wasn't in the palette that we had available to us and we were simulating that color using dithering, well then you end up having stoppy-startiness. You know, the expanses of color are broken up. You can imagine if we were simulating a shade of light blue by using a light blue, a very light blue and a very dark blue in a chessboard pattern, the scope there we would have had for run length encoding is now gone because the dithering is making it go light blue, dark blue, light blue, dark blue, light blue, dark blue, light blue, dark blue. So sometimes in a GIF, the benefits you would expect to get from reducing the number of bits per pixel and faking the missing colors using dithering are outweighed by the fact that you screw up the run length encoding. So sometimes when you reduce the number of colors in a GIF and resort to dithering, you don't get the benefits you thought you might get because you have run length encoding in the mix as well. So that could be quite interesting, and you might see some evidence of that in your images with your GIFs. GIFs can have one transparent color. So If, for example, you wanted this lion image to appear on a page and there was a pattern on the background of the page and you didn't want the rectangular edge to be visible, you could make one color in a GIF transparent. In practice, it tends not to be very satisfactory, because if we get time, I'll talk about transparency a bit more in another class. But it turns out that for things to go smoothly, you actually don't want you often don't want just 100% invisibleness or visibleness. You want degrees of visibility. So it's possible, but generally it's not very satisfactory. Progressive coding is very interesting. Again, it's one of those things that people like me used to worry about in the early days of displaying images on computers and in the early days of the internet, and now it's not such a big deal, but it is interesting to know about it. When we look at a web page now, as before, the HTML is downloaded. If that HTML file contains links to images, then the browser goes off and requests those images from the web server, and then they come back and they're integrated into the page. In the early days of the internet, that didn't appear to happen instantly. The HTML file downloaded, you could see the text of the page, and then it would go off and get the images, and the images would actually download on the page before your very eyes while you were looking at it. A lot of people had their browsers set up in such a way that they didn't even automatically download the images. You just got an icon telling you there was an image there, and then if you actually wanted the image, you'd click and go get it. The experience you have of looking at a web page now is that it all happens and all arrives instantly. It still doesn't happen instantly, it just happens so quickly it appears to. But in the early days of the internet, you would actually see the GIF, materializing line by line. So that was quite frustrating. So people devised progressive coding schemes, and they're quite clever because progressive coding allowed you to get an overall impression of the whole image before it was completely downloaded. So let me give you an example. So if this is a progressive download, very early on in the image, we have an impression of the overall image. So we can see all of the image quite poorly. By the halfway point, we can half see all of the image. And as the download progresses, the image becomes more defined, I suppose is the word. So by the time it's fully downloaded, we have the full image. With a regular download, at the halfway point, we can fully see half of it, which is not the same as being able to half see all of it. Now, it turns out that a progressive download isn't any faster than a regular download. In fact, often there's even some small overhead for the way it's coded. But the wait doesn't feel as long. And that's not trivial.
On the first one?
On the first one, yeah.
Yeah,
so, like, this doesn't, an image downloading this way doesn't feel as slow as an image downloading this way, even though it's no faster and may even be a fraction slower. But it turns out that in the world where people are used now to web pages materializing instantly, how people actually feel about the wait is not trivial. And so people have done experiments, for example, with how long someone is prepared to wait for something. It turns out we actually adapt our expectations, and we'll wait longer for something to appear on our phones before clicking and giving up than we will on our screens, for example. But you can imagine in an e-commerce situation, if people have many choices, the appearance of something downloading quickly or slowly is going to have an impact on whether you might ultimately make sales or not. So progressive coding is also one of those things that I thought I was done with. But by the time back when I thought I was never going to have to worry about progressive coding again because the internet was getting so fast, I had never imagined, giving out about the data transfer rate to my mobile phone. And we actually have quite fast rates in the cities in Ireland anyway, at least. Whereas in some parts of the world, and in the US in particular, people's bandwidth is actually quite constrained. And so making people feel like they're not going to have to wait so long is not a trivial thing. So GIF allows for progressive downloads as well. And it just does that by actually just altering the order of the lines. So instead of going line 1, line 2, line 3, line 4, line 5, it does like 1, 5, 9, and then comes back and does every fourth one again and then fills them in. So it's actually quite simple in the way it does it. And for the most part, it doesn't break the run length encoding mojo either. So that's that really. That's all I have to say about GIF, I think. So in the next class, I'll talk a little bit about transparency, and I'm going to talk an awful lot about JPEG. So JPEG is important. After that, I want to talk about MPEG, how video is coded, and then after that, I don't know yet.